Hi, folks. This week we're going to be talking about measures of variability. You may also hear me use the word dispersion. It really means the same thing, right? We're talking about how data are spread around in the data set. We're going to cover the tyranny of the mean. We'll talk a little bit about how we define variability, and then I'll spend some more time giving you some common measures of variability. And then lastly, we'll talk about how to calculate that variability. Those last two steps are going to be intertwined. We'll talk about each measure and then we'll talk about how to calculate it. When I say tyranny of the mean, what I mean is that the measures of central tendency that we calculate, they tend to obscure differences between different samples. They can obscure the variation that exists within one sample. Each one of these pictures here shows a sample that would actually have the same mean if we take distance from the center of the bar as some meaningful value. Each one of those would balance at about the center of the beam, which would mean they would have the same measure of central tendency. But you wouldn't know that. You wouldn't know that they're very different just by looking at the mean. In order to get a more complete picture, we have to take some measure of the variability itself. There are a number of different ways that you can define variability, like what that term means itself. I'll give you two here that you can think about. You can consider variability to be some measure of how data are dispersed around that measure of central tendency that you calculated. Another way to think of that is that variability gives you some estimate about how precise that measure of central tendency is. If your data are more variable, your measure of central tendency tells you less about the data set. Here I've listed out a number of different measures of variability that are commonly used. I will go through and describe each one of these here, and you'll notice that on the right, I mentioned that I'm just going to give you a note about nominal data. I'll tell you up front, the measures of variability that we're going to cover in any depth in this particular recording, they cannot be used on nominal data. Those measures are the range, the interquartile range, the sum of squares, and some of its derivatives like variance and standard deviation. The range is very easy to calculate. All you need to do is to take the highest value in your data set and the lowest value in your data set, and you subtract that low value from the high value, and that value you get back, that is the range. It only considers two data points in your entire data set, and so as a result, it's one of the least informative measures of variability. You can just picture this for a moment. I can know how far apart the two very farthest data points are, but perhaps a lot of my data are clustered in the center, and those two data points that I measured are pretty much outliers. The range doesn't really give you a sense of how far away each one of the data points are, just how far apart the extremes are. And again, we're talking about subtraction. If we're going to be doing that kind of math, we need to know something about the interval between values. That interval has to be meaningful, which means we have to be dealing with interval or ratio level data. You cannot calculate a range for nominal or ordinal data. I'm going to take this time to remind you to think carefully about the data that you're working with before you plug them into SPSS and ask SPSS to do some math for you. With the range, it is a simple calculation. It is the maximum value minus the minimum value. And you should not do this if we are dealing with ordinal or nominal data. But I just want to point out that depending on how you've collected your data, it may not be obvious to SPSS that it should not calculate something like a range. If you have encoded your data, perhaps you have nominal variables, but you've encoded them numerically, it is entirely possible for you to calculate a range, but the value that you get back is not useful, is not meaningful. The same goes for ordinal level data. Be very careful in determining what level of data you're dealing with before you go calculating any of your summary statistics. Now let's talk about the interquartile range. The interquartile range, as the name implies, is telling you something about the range between two quartiles. Specifically, it's telling you what's the space, the distance between the value at the 75th percentile and the value at the 25th percentile. Because of this, because we're working with these quartiles in just the middle 50%, the interquartile range is resilient to the effects of outliers. Just like when we were dealing with calculating a median, if we're going to get quartiles, we have to sort our observations in increasing order. Then we can find the 75th and 25th percentile. We do the subtraction, and that is our interquartile range. Remember, it only considers the middle 50% of your data. So if we have the opposite situation to what we described before with the range, we have some data in the middle and we have a couple extreme values on the ends. The interquartile range, or if you divide it by 2, the semi-interquartile range, is not going to pick up on the variability at those extremes. And since we're talking about percentiles, we need to at least be able to order our data. So we need to at least have rank or ordinal data if we're going to calculate an interquartile or semi-interquartile range. You cannot use the semi-interquartile range for nominal data because we cannot order those data. I want to familiarize you with the notation that I'm using here. You will see IQR and SQR, IQR meaning interquartile range. Some books will have IR, and then SQR I have for the semi-interquartile range. Some books may only have SR. So for the interquartile range, if you look at what I have here, that X sub 75 indicates the value at the 75th percentile, and similarly, X sub 25 indicates the value at the 25th percentile. We're going to subtract those two to get the interquartile range, and then if we want a semi-interquartile range, we'll go ahead and divide that by 2. While the sum of squares may not be particularly familiar to you unless you've done statistics, some of its derivatives probably are. The standard deviation is probably the most familiar of the measures of variability for folks who are not doing statistics. That standard deviation, the variance, and the sum of squares all depend on us summing up or adding together the squared distances of observations in the dataset from the mean of that dataset. What that means is the sum of squares and all its derivatives consider every single observation in the dataset. And that can be very powerful and very helpful because unlike the range or the interquartile range or semi-interquartile range, we will know something about data close to the mean or close to whatever measure of central tendency we're using, as well as those much further away from that measure of central tendency. On the downside, it can be very sensitive to outliers. Perhaps the only measure that would be more sensitive to outliers would be the range because it depends on the extremes. Because of the math we're doing, because we have to add values together, because we're going to have to do some dividing, we need to be working with interval level data or ratio level data. We cannot use ordinal or nominal data to calculate the sum of squares or any of its derivatives. I wanted to take a moment and sort of visualize how the sum of squares works. As I mentioned, we're looking at the squared distances from the mean. So we have to figure out where our mean or our balance point is here. When we're calculating the sum of squares and its derivatives, we are using the arithmetic mean, right? And we're measuring the distance of each observation from that mean. But then we need to do that for every single observation in the data set. We're going to square each one of those distances, and then we'll add them together, and that will give us our sum of squares. And we can go from there to calculate the derivatives. Let's just go through this notation here just so that you have it in mind when you see this in your text, or when you go to put pen to paper to try to calculate some of these statistics. At the top, we have the sum of squares. This is sort of the core for all of the other statistics here. So that giant sort of E-looking thing, this is a Greek sigma, for those of you who have not been looking at Greek notation. And in the parentheses, we have X with a bar on top. You will hear me call that X bar. That represents the mean. And then we are subtracting from x bar x sub I. This is some observation. And that starts with the first observation, I equals 1, and goes all the way up until we get to the last observation, where I equals whatever the size of the sample is. So to calculate a sum of squares, we will simply subtract each observation from the mean, square that value, and then we'll do that for every observation in the data set before summing all of those square distances together. And that is the sum of squares, which I will continue to note as SS. If we go a step further, we can calculate a variance. The variance is that sum of squares divided by n. So what we're saying is, what is the average squared distance from the mean? And then finally, if we want to get something that is in terms of the units that we are actually interested in, we can take the square root of the variance to get the standard deviation. A quick note on measuring variability in nominal data. It is something that we can do. We have different ways to estimate variability. Again, we're thinking of variability as some measure of how precise our measure of central tendency is, right? And so in nominal data, we can calculate a mode as a measure of central tendency. That'll tell us what the most popular category is, right? Then, if we're going to measure how precise that is, that would be like saying, well, if I have all of the observations in a bag and each observation belongs to a category, maybe it is a green observation, a purple one, or an orange one, and I know my mode is purple, well, if I reach into the bag, how likely am I to pull out a purple, right? And the more representative that mode is of the population, the more likely it is you're going to retrieve that category each time you reach into the bag. So instead of measuring range or interquartile range or some measure of a sum of squares, variance, so on and so forth, we can't measure those in nominal data, right? Because we don't know the distance between observations. There's no intrinsic value in each one of these categories. So instead of doing that, oftentimes we'll calculate some type of diversity index. And so you can think of diversity indices like this. High diversity would be the case where every category has the same number of observations. If we keep the same number of observations, a less diverse sample would have more observations in one group and fewer in others. And so measures of diversity or diversity indices use different methods to calculate what the diversity might be given the distribution of observations among categories. You won't use this in this course, but there are times where you may want to know, you may want to or have to deal with nominal data. If, for instance, we want to know if a certain methodology is more accurate at diagnosing particular psychoses than another. We would need some measure of central tendency, a mode, what was the modal diagnosis for the same symptoms, and then we'll need some measure of variability, and that would be where our diversity indices come in. So to summarize, we can describe our data using a measure of central tendency to tell us where the center of our data are, how we could balance those data if they existed on some beam. But the measure of central tendency alone is not enough. You can have an infinite number of samples that have the same central tendency, but different variability. The data are spread out differently within those samples. And so we use measures of variability to try and understand that dimension of our data. Central tendency and variability are not the only measures that we use to describe data, and we will try to talk about some of those other measures as we move forward. Okay, folks, that's the end of this particular video. I hope it's helpful in getting you started with understanding measures of variability or dispersion. In the next video, I'll show you how to calculate some of those measures of dispersion in SPSS. Before you say it, yes, I'm aware that I showed you a little bit of that in the last video for last week, but I just want to reiterate and specifically focus on those measures of variability. So it'll be a very short video, and hopefully it'll give you the tools that you need so that you can calculate those measures as you do your homework and your next quiz. As always, if you have any trouble, if you have any questions, please reach out. I'm just going to remind you here, please use email. Email me at ca923@drexel.edu. Please, please, please do not use Blackboard. For whatever reason, I'm not getting those messages. See you next video.